Oh boy, here's a really fun question. Talk about quantum mechanics and entanglement. Well, I'd be happy to. I did my undergraduate in math and physics, and then I did a master's degree in physics before I got my PhD in nuclear engineering. And I have published a lot in quantum mechanics. Largely, it's indirectly because I do electron paramagnetic resonance research, which is a very quantum mechanical effect. And so there's a lot of quantum mechanics in that, and also in luminescence. I do dosimetry, radiation measurements with that kind of thing. And so I do a lot of research with quantum mechanics, but I've only really published one or two papers that are really quantum mechanical. Like, for example, that neutrinos, their oscillation could be explained by entanglement. And so that begs this question, well, what is entanglement? Well, let's start off with quantum mechanics. Quantum mechanics, the way that I would describe it is that it requires a mathematical formalism. So you just really only need undergraduate differential equations. To solve Schrodinger's equation, that's it. You just need to be able to solve a differential equation. And the point is that allows us to predict measurements. Now, to say that Schrodinger's equation is physical is something that is probably more of a philosophical question, but to be able to predict what you measure, you use Schrodinger's equation. And you calculate the Hamiltonian, and that allows you to predict what you measure. So as an experimentalist, a scientist, that's really all that matters to me, is that I can predict what I measure. I can explain what I can measure so I can mitigate it, control it, and take advantage of it, and being able to do things, and controlling nature in whatever way we see fit. And so the point is that quantum mechanics allows us to predict what we measure. If you ascribe anything more to it than that, there's really not a good technical basis for it unless it's in philosophy. Entanglement, that's a hard one in the sense that you want to think of it classically. Like, you want to think of it as like having a red pill and a blue pill in the same jar, and then if I separate them, I don't know which one they are, and I open one, and I know what pill is in which side, then I knew what the other one was, and they were untangled until then. If you use that kind of analogy, you'll get a lot of wrong answers when it comes to quantum mechanics. And the same thing applies with like angular momentum. Angular momentum is quantized, just like energy is quantized. So that you can have an atom that's got an electron that's in an orbital that's basically stationary. It's not moving, but it's got angular momentum. And that angular momentum is going to be quantized along with its energy. And so what it comes down to, I would say, in my opinion, it comes down to the equations. That's how I would interpret it. The equations allow me to interpret what I measure and to predict what I'll measure in a given scenario, allowing us to do, say, solid state electronics and things of that nature. And so quantum mechanics, I would say, it's finding a way to come up with an explanation for what we see in terms of a mathematical formalism. You can be philosophical and come up with many worlds hypothesis, but I would say that's silly because there's no experimental evidence for that. It's just saying there's more. It's pouring more into the equations than we get observationally. So that would be my take. I hope that helps. If you want to see my paper on explaining why neutrinos are actually oscillating because of entanglement effects as they travel through the universe and getting entangled and so therefore changing what you can measure in terms of their flavor, I'll put that in the comments. Reference to it right there. Fun paper. I loved it. I'm just a nerdy geek, and so I do those kinds of things. But I hope that helps. Hope you enjoy the video. I don't know. Have a good day. Thanks for watching. Bye.